Welcome back, everyone, to your final exam review explainer. I'm your host, and today we're tackling the big one. We are covering the absolute ultimate culmination of cellular energy, oxidative phosphorylation. Seriously, this is the grand metabolic finale where everything we've talked about all semester long finally comes together to generate the power that drives life. So grab your notes and let's make sure you're completely ready to ace this test.
Here's our syllabus for today's review session. We're going to start with the ultimate energy culmination, break down the big three similarities, review some key chemoosmotic milestones, map out the membrane complexes, trace the electron path from NADH to oxygen, and wrap it all up by calculating the final energy payoff.
All right, kicking things off with Section 1, the ultimate energy culmination.
Okay, I can practically guarantee you're going to see a test question asking you to compare these two highly efficient processes. Let's break it down. First, oxidative phosphorylation is the absolute grand finale of aerobic metabolism. It happens right in the mitochondria of eukaryotes, and it involves reducing oxygen to water using electrons donated by NADH and FADH2. And here's a key distinction. It works equally well in the light or the dark. On the flip side, we have photophosphorylation, which takes place over in the chloroplasts. This process oxidizes water to oxygen, uses NADP+ as the ultimate electron acceptor, and crucially, it absolutely requires the energy of sunlight to work. But despite those differing inputs and environments, these two processes are fundamentally connected.
Moving right along to Section 2, the big three similarities.
Listen, if you only remember one thing for this section of the exam, please burn these big three mechanistic similarities into your brain. First up, both of these processes rely on the flow of electrons through a chain of membrane-bound carriers. Second, they both couple the downhill or exergonic flow of those electrons to the uphill transport of protons across a proton-impermeable membrane. Basically, that's what conserves the free energy of fuel oxidation as a transmembrane electrochemical potential. And finally, number 3, both systems use that exact transmembrane flow of protons as they rush back down their concentration gradient through specific protein channels to provide the free energy needed to synthesize ATP. And they do that via the incredible membrane protein complex we know as ATP synthase.
Let's jump into Section 3, chemoosmotic theory, biological milestones. Way back in 1813, Claude Bernard dropped this piece of wisdom. If an idea presents itself to us, we must not reject it simply because it does not agree with the logical deductions of a reigning theory. It's so true, right? Paradigm shifts require completely open minds. And that brings us to Peter Mitchell's groundbreaking hypothesis from 1961, which, believe it or not, faced massive opposition at first just because it challenged the popular thoughts of the time.
So, here's the crucial definition you must write down, the chemoosmotic theory. Mitchell proposed that the transmembrane differences in proton concentration are literally what act as the reservoir for the energy extracted from biological oxidation reactions. Think about that. The once radical idea that a proton gradient itself could be an energy reservoir is now fully accepted as one of the great unifying principles of 20th century biology. Actually, as Mitchell himself joked in his 1978 Nobel address, even his fiercest critics eventually promoted his idea to the status of a widely accepted theory.
Let's dive into Section 4, Journey Through Membrane Complexes.
You've got to appreciate the brilliant experimental method shown here. How do we actually know these distinct complexes even exist? Well, scientists essentially performed a molecular teardown. First, they stripped away the outer mitochondrial membrane using a detergent called gigatonin. After osmotic rupture gave them fragments of the inner membrane, they gently dissolved those fragments in a second detergent. Then, using ion exchange chromatography, they physically isolated the protein mixtures. They managed to resolve 4 unique electron carrier complexes, which we label with Roman numerals I through IV, right alongside the ATP synthase. This was the tangible proof that these carriers are organized into massive, membrane-embedded supramolecular complexes.
All right, Section 5, Electrons, from NADH to oxygen. This graphic beautifully illustrates the start of what is basically the ultimate biological relay race. Notice how the electrons have totally different starting lines depending on their biological source. Electrons from NADH pass through complex I, while electrons from succinate enter over at complex 2. Other sources, like fatty acyl-CoA or glycerol 3-phosphate, have their own dedicated entry enzymes on the membrane. But look at the arrows. It doesn't matter where they start, they all converge. They all ultimately hand the baton to the vital lipid-soluble carrier, ubiquinone, which we usually just call Q.
But hey, the journey doesn't stop at Q.
From ubiquinone, complex 3 catches the baton, coupling the transfer of those electrons to the pumping of protons, and then hands the electrons off to cytochrome C. Think of cytochrome C as a mobile shuttle bus, delivering those electrons straight to complex IV for the grand finale. Inside complex IV, which is this massive 13 subunit enzyme, molecular oxygen finally receives the electrons and is safely reduced into water.
Bringing it all home with Section 6, the final energy payoff.
Okay, big question time. What is the actual energetic payoff of this entire crazy electron journey? When a pair of electrons runs the gauntlet from NADH, traveling all the way through the complexes to finally rest in molecular oxygen, exactly how much energy is released and conserved in our proton gradient?
Boom! The answer is negative 220 kilojoules per mole of NADH. The standard free energy change here represents a massive, highly exergonic release of energy. Let's look at the math on the board real quick to see exactly how we derive that number. Using the standard reduction potentials of our electron pairs, the overall change in potential comes out to 1.14 volts. When we plug that into our free energy equation, multiplying our two electrons by Faraday's constant and our voltage, it mathematically proves we generate 220 kilojoules of energy per mole. In a biological setting, that provides enough free energy to generate about 2.5 molecules of ATP for every single pair of electrons passing to oxygen.
I'm going to leave you with a take-home prompt to chew on before test day. The source texts actually point out that in actively respiring mitochondria, the real free energy change is substantially greater, meaning it's even more negative than that standard 220 kilojoules per mole we just calculated. So considering how beautifully efficient and optimized the cellular machinery really is, what do you think might be the absolute limit of life's ability to harvest energy? Think deeply about how these incredible molecular machines operate and how they quite literally power everything we do. Good luck studying, everybody, and I will see you at the exam.